Okay. Good evening, everyone. My name is Farhad Shahnia. I'm from Murdoch University, and this year I'm the secretary of the Industrial Electronic Society's WA chapter. Today, August 26th, we are having the 5th seminar that has been arranged by the IES WA chapter. The title of the talk is a very interesting topic and very timely topic for our power sector, the battery energy storage placement and utilization in unbalanced distribution networks. Today's speaker is Associate Professor Xiangjing Su from Shanghai University of Electric Power. Dr. Su has received his PhD in electrical engineering from Curtin University in 2015. He was awarded a China Scholarship Council program for conducting his PhD studies at Curtin University. After graduation, he joined Shanghai University of Electric Power, and then he was selected into the Shanghai Puijiang Talent Program in 2017. Dr. Su is currently with the School of Electrical Engineering and Telecommunication at University of New South Wales as a visiting professor, which is also supported by the Shanghai University of Electric Power's Academic Star program. His main research interests include optimal planning and operation of active distribution networks and artificial intelligence applications in offshore wind farms. Dr. Su has published so far more than 40 research papers in these fields. He was the technical program chair for the 9th International Conference on Power and Energy Systems, ICPS 2019, that was held last year in Perth. And this year, he's the subject track chair for the upcoming International Conference on Smart Grids and Energy Systems, SGES 2020, which will be held virtually from Perth in the last week of November this year. He's an IEEE senior member and has served a couple of journals as editor and guest editor, especially the most important one, the IET Generation Transmission and Distribution Journal. Over the past 5 years, Dr. Su has secured close to 2.5 million Chinese yuan for research funding from government and industry. So today, Dr. Su is with us. He's going to share his experiences and research outcomes with us in the field of battery energy storage in distribution networks. So thanks very much, Dr. Su, for accepting to deliver a talk for us, and the floor is yours. Thank you.
Thank you, Farhad. Good evening, everyone. I'm Xiangjing Su from Shanghai University of Electric Power. Before I start my presentation, I want to give my thanks to the organizers, Professor Farhad, Mayed, Amir, for the kind arrangement, and also for everyone. I know it's dinner time right now, probably in Perth, and thank you so much for your time and attendance. Hopefully you will enjoy this presentation. So today I will talk about our latest work on the battery energy storage placement in unbalanced distributed networks. So before I start the technical presentation, I want to go quickly through this university group and myself information. Our university is Shanghai University of Electric Power. I think next year we will celebrate its 70 years birthday. And our university is jointly operated by the central government and the Shanghai government. We have two campuses. One is in the downtown city, you can see here, the Yangpu campus, and the other one is the Pudong campus. Right now, this campus in Lingang, which is a part of Shanghai Pilot Free Trade Zone. We have 12 schools or departments and totally over 12K full-time students. Of course, in the past several years, we have hosted or won many awards or projects. So I'll go to the details. Then it's about our group. So our group is in the center, in the Shanghai Engineering Research Center of Green Energy Integration Technologies. So we have 13 full-time research staff. Among them, 4 professors and almost half with overseas research experience. And we have a big group of students, over 70, and still expanding right now. And the group leader is Professor Yang Fu, who is the vice president of our university. And in our center, we have 2 research domains. And the first one is the planning operation of distributed works. And then it's the control and maintenance of offshore wind farms. So yeah, we have published some papers, including the IEEE Trans journals. And I want to emphasize that last year, we just won the prestigious National Scientific and Technological Progress Prize, second class. And this is really important one for us. The contribution is on the wind farm energy. So about myself, I think just now Fahad has given the canned introduction. I won't go to go about it, but I want to take the chance to thank my PhD supervisor, Peter Wolfs, who has just retired last month, happily, from CQU as the Central Queensland University. So thanks, Peter, for everything he has done for me. So this is the outline of this presentation. I will start with the background and motivation. So we know that renewable is getting more and more available to us. I think especially in WA, most households has the rooftop PVs right now. Yeah, this trend brings about great economic and environmental benefits, but you can see they may adversely affect the operation and planning of our grid because of its intermittence and uncertainty. So as the promising solution, battery energy storage system can act as an energy buffer and decouple the time and generation and consumption, so that we can storing the cheaper and cleaner off-peak generation and release it during the peak periods. So right now, battery has many functions for the grids. Here I listed some typical functions here. For example, grid investment deferral, congestion relief, voltage regulation, reliability and resilience enhancement, and renewable energy sources integration, hosting capacity improvement. So I want to say it's only part of them. So the function is expanding. So for these functions, we know they're very good, but to be available to us, we want to consider the costs. It's well known that in the past decades, the cost of battery has been going down and down, but still the costs is the barrier for daily use, for residential use. So the benefits listed above are associated with its optimal placement. So what is the battery placement here? Generally, placement involves the optimal selection of battery technology type, installation location, size, and also the charging discharging power, with a target to minimize the net benefits with the physical operational constraints respected. So this is a definition of placement. It is important for the battery utilization. And let's see why we do this study. based on our research on the past, literatures, we found the following challenges. So I will go through them one by one. Firstly, current battery placement studies are commonly based on a balanced network model. But we know that the real systems are unbalanced, especially at the feed end. So if we do the battery placements based on a balanced network model, the solution may be less effective, or even unreasonable. So this is the first challenge. The second challenge is on the sensitivity analysis. So we know that the battery placement is very complex and time-consuming. So normally in practice, to reduce the computation burden, we perform sensitivity analysis. And when we do this, we need the sensitivity indices. But if you see the papers or past researches, we can find that all these indices are based on the power injection model. That's only the discharging. But the battery is different from other components. It has both charge and discharging, and the impacts are contrary. So to reduce the loss of network loss, so we must consider both for a renewable solution. And lastly, sensitivity-based battery placement studies usually perform the sensitivity analysis once. You perform the sensitivity analysis once and select a desired number of placement locations. But we know that if you do the analysis once, all the selected locations are electrically close to each other, and the solution will be less cost-effective, and normally in the form of a clustered solution. They are together. So to address these challenges, we did the work below. So I will start with first one. We first proposed a comprehensive battery placement model to minimize the costs of primary investment and operation maintenance, whilst maximizing the saving by loss reduction and load shifting. And this problem defined is an optimal power flow problem. So we propose to solve it by the combined solver of heuristic particle swarm optimization and also the direct load flow. But this is only the optimization model. But how can you use it for complex situations, such as our case, the unbalanced network of high DG penetration? How to use for these cases? Yeah, we need the sensitivity analysis. But the sensitivity we have mentioned before, all injection based. So here, to consider both charging and discharging, we propose a comprehensive loss sensitivity index. And on this basis, CLSI is a comprehensive loss sensitivity index based sequential placement strategy is presented. So finally, we carry out simulations on real Australian network to test the proposed placement model and strategy. So this is the brief walk. I will go to the details. So this is the proposed comprehensive battery placement model. As we said, it's an optimal power flow model. So it includes the optimization objectives and also its constraints in the next page. So if you see this optimization objectives, its objective function includes 4 components. The first 2 are the costs, and the last two are the saving. So it's the cost minus saving, that's the net costs. So we want to minimize it. So if you see the first one, CPI, we call it cost of primary investment. So it includes the cost of battery and its associated inverter in the form of net present value. This is the CPI. And of course, when you put it into operation, there's another cost of operation and maintenance. So in this definition, you can see the COI includes the fixed value and the variable value. So if we see the right side for the saving, saving by loss reduction, we define as SRR. That's the loss difference before and after the battery installation. The last one is the saving by load shifting. That is the price difference of the shifted energy. So this is the four components of the objective function. Here are the constraints. The first constraints we consider the power balance constraints. That means, in the system, the power flow at each node should be equal. Specifically, we consider the battery power, DG generation, load, and also the power from the grid, the network power. And for this network power, I want to emphasize that it's an nonlinear form. We should pay attention to this part because later we will return to this equation. The second constraint is about the energy balance constraints. That means per day, the charged energy should be equal to the discharged energy. We have the voltage boundary constraints and also the boundary on the decision variables. In this study, we are going to control the capacity and also the charging discharge power. For this capacity, normally it depends on the project target and also budget. For this power, it's limited by the inverter capacity. So the next constraint is about the load shifting constraints. Why we consider this one? Because we know a battery is expensive. So when we have the battery, we want it to have multiple functions. Instead of only load shifting or loss reduction, it can be used for other purposes. So we must reserve the capacity for emergency use. Also, we know this is a study on an unbalanced network, so the voltage unbalance factor should be limited. And also lastly, the SOC limit to avoid over discharging or charging. So this is a constraint size. So these objectives plus the constraints form an optimal power flow. And we know that optimal power flow incorporating AC power flow equations is very complex. It is mixed integer, nonlinear, then convex. The main reason is here, is the constraint here, nonlinear. So its solution is very challenging, both in theory and in practice. So if we see the past research, we may find that there are generally three categories of solution methods. The first one is mathematical programming. That is convex optimization. So in this method, we transform the non-convex problem into convex one, which can be solved by the commercial solvers such as GAMS or Cplex. And the process of transforming non-convex to convex, we call it convexification. And this process requires some assumptions or approximations, such as here, the relaxation of the domains or linearization of the distribution load flow. So this is based on assumptions. So the accuracy is reduced, and also the global optimal capability is lost. But we say convex optimization is efficient, reliable, and robust. So I personally believe it's really suitable for the control purpose. But when it comes to our study placement, there are two main barriers. So the first one is the linearization of the unbalanced distribution power flow. So this is currently, I think, unsolved. Still difficult to work on it. In the past several months, we have worked on this and we have made some progress. And the other challenge is handling the discrete placement variable. Because if you see the convex optimization, it requires the object function to be differentiable in the convex domain. So if you introduce discrete variables, the computation burden will increase significantly. So here are the two challenges. And also considering these drawbacks, we will turn to the heuristic search. So the second one is called heuristic search. I think most of you may be familiar with this method. It's based on the evolution theory. We know some famous algorithm like the genetic algorithm. Particle swarm optimization methods belongs to this category. For this category, it has theoretical advantages in handling non-convexity, non-linearity, and discrete variables, because it's free from all these barriers. And also for this heuristic search method, if you set proper parameters, you have the capability to converge to global optimal. Generally, we say heuristic search is computationally intensive, but considering our study's placement can be done offline, so its performance is acceptable for our purpose. So this is the heuristic search, and there's another one here called hybrid algorithm. And this is a very latest one, and you may find some papers, not so many, because this is really new. And the principle is to combine the mathematical programming and heuristic search to overcome the drawbacks of each other and to demonstrate an improved overall performance. So I want to get more information here. If you are interested, you can search online. Yeah, as we said, in our research, we propose to solve the problem using the PSO and the DRF for direct load flow. Here is the flow chart. If you see the figure 1, we employ PSO as the global solver to update and determine the decision variables. And then we use the direct load flow to support PSO by assessing the fitness of its particles and also against the constraints. So yeah, so the Previous slides covers the proposed optimization model, but how to use it for unbalanced high penetration cases. We should consider the sensitivity analysis. And the first, but also important issue is the definition of an comprehensive loss sensitivity index. So here we consider both charging and discharging impacts and define such an index. We call it CLSI for comprehensive loss sensitivity index. And the definition, the calculation formula here for this equation, we have two ways here, lambda D and lambda C. Lambda D and lambda C are the ways for the charging and discharging loss sensitivity. Usually we can decide the value flexibly according to the real needs. Ensure their sum equals 1. And if you see this equation, lambda D is plus, lambda C is minus. This is because our purpose is to reduce the loss. Discharging, we know, is like generation, so it helps reduce the loss. So that's a plus here. But for the charging, it is demand for the grid. It increases the loss, so we give a minus. That's a combination for this CLSI. So based on this, CLSI definition, we propose this sequential placement strategy, including these 6 steps. The step 1, we calculate the CLSI for each phase of all buses. Then in step 2, we get the average value of 3 phases as the equivalent value for the bus. In the next step, we can find the bus with the highest loss sensitivity. Then in step 4, we perform the proposed comprehensive optimization to decide the optimal battery rating, charging discharging power for this bus. But we know the results from step 4 are for per phase. They are different, among 3 phases. But commercial products on the market do not have different per phase ratings. So we get the final results, the final rating as the sum of the 3 phase values. So the whole process from step 1 to step 4 can be repeated until we get a desired number of batteries installed, or the net benefit deteriorates. So this is the strategy. It helps to utilize our proposed placement model. So in the next section, we will test the performance of the proposed model and strategy and on a real system. So here is the system. It is collected from the Port Solid City project, and I think its location is in Forest Field district, not far from the Perth International Airport, quite close to the airport. So it is a 415 volts network with 101 buses and 77 consumers. Among consumers, 51 are single phase and 34 has a single phase rooftop PV systems. So we have a penetration around 32%. So this is the system. We also designed 5 cases to test our performance. So I will go through these cases one by one. So in the case 1, we simulate the proposed CRSI-based sequential placement to test its effectiveness. So the results is given in table 5. If you see this table, it's very interesting. So now buses 83, 74, 92, and 19 are selected for the first 4 sequential placement. And also you can see the objective function is continuously reduced. But the reduction is become less with the placement goals. This is because, you know, at the beginning, probably the saving is dominant, but with the placement going on, the costs will become dominant. So we are looking for the crossover point. That is the optimal placement. So where is it? If you see the 5th placement here, very interesting. The result here is the same as the 4th placement. That means if you place another battery at the bus 51, it will cause the loss of net benefits. That means it is financially infeasible. So for this network, the optimal placement 4. Totally you need 4 batteries installed, and with the details here. And in the case 2, and also the case 3 later, we want to show the superiority of this proposed strategy over the traditional clustered placement and also the traditional injection-based loss sensitivity index. So for this case 2, so case 2 is based on the clustered placement strategy. So what is it? That means the placement locations are selected simultaneously based on once-off sensitivity analysis. That means you do the sensitivity analysis once only, and you select 4 locations simultaneously. And you can see the result here. It is 83, 81, 79, 80. Probably from the number is not so clear, but if you see the figure, the network, so 81, 83, and 79, 80, they all at the feed end all together. Because, you know, they are at the feed end, they are electrically close to each other. So it's unreasonable. But if you see our proposed solution, that's 83, 74, 92, and 19. So it's quite different. And also the results are different. You can see the battery placement by the clustered strategy is really conservative. You can see the energy and the power quite limited. The reason is because they're too close to each other. And for the case 3, we are going to show the superiority of the proposed comprehensive loss sensitivity index over the existing injection-based RSI. So if you see here, right now the 4 locations are, are 83, 79, 90, and 74. It's also different from the proposed solution. And we say the proposed, by comparison, you can see the proposed is more spatially distributed. Of course, I have the figure here. If you see this figure, this one is the proposed one, and this one is the existing ejection-based RSI. We can see that our proposed is really more spatially distributed. And regarding the reason, I have mentioned about the reason, because we know discharging means generation. So the most sensitive always at the feed end. But if you consider charging is the demand. So the least loss increase is at the feed beginning. So we'll consider charging and discharging. So that means it will push the sensitivity profile backwards to the very beginning. So that's why we have such a solution. And also, if you see the economic, results here, very interesting. Almost all the results are the same. But if you see the loss reduction, you can see our proposed solution is much better because we consider both charging and discharging. So this is case 3, and case 4 and 5 are for the impacts analysis of key factors, because this study is for the unbalanced active distributed networks. So we should consider how much impacts the unbalanced can have, how much impacts the DG penetration can have. So in case 4, we consider the voltage unbalanced factor. We reduce the upper limit from 2% to only 1.2%, and we can find the result here. So we see with the harsher voltage unbalanced factor limit, the charging and discharging for the first placements are limited. This is to avoid, too much power variation among 3 phases. That is to avoid voltage unbalanced factor constraints violation. But for the placement afterwards, we can see they become more dynamic, more active, compared with our proposed one, with a similar overall placement solution. So this is for the unbalanced impacts analysis. For case 4, this is case 5. For the case 5, we want to investigate the impacts of DG penetration. So how about we increase the penetration by 100%, that is doubled. So we can see the solution here. So with the hair penetration, we can see the selected buses of CLSI are similar, but the results are quite different. The higher the DG penetration becomes, and the more improvements on the solution we can get. This is because we have more energy to be shifted. And in our module, we define the object function as the saving of load shifting. So more shifted, more revenue. This is why we have a more active solution here for the higher penetration. So yeah, the last 5 cases are for the economic analysis. Of course, it can also, consider the operational performance. This is the performance of the operation for this network. We listed all the final solution for all 5 cases. We can see all the performance has been improved. But there's a question here. In the previous module, we didn't consider voltage magnitude, voltage unbalanced factor, peak value difference as the objective. We only consider as the constraints. But why they are optimized? If you see here, really every case, these factors are optimized. The reason, what is the reason? So this is because, for the loss reduction, it is affected by the voltage and unbalanced profile. For the load shifting, it is associated with the peak value difference. So when we optimize this loss reduction and load shifting, you also optimize the related voltage, unbalance, and the peak value difference. So this is why our performance is also optimized at the same time. So yeah, so from this module and analysis, we can get the conclusion here. So firstly, the proposed comprehensive battery placement optimization and its optimal power flow solution method are feasible and effective for our unbalanced distributed networks of high DG penetrations. The second one, the defined CRSI is superior over the existing injection-based RSI in loss reduction. And also, the proposed sequential strategy is superior than the existing clustered placement strategy. When we impose a harsher VOI limit, we can see it is harsh only for the first placements, but for the remaining ones, the impacts are mild. And lastly, if we have higher penetration of distributed generations, we can see we have more energy to be shifted, and with a higher saving by load shifting. So this is the conclusion from this study. Of course, we can move forward based on this study. So here are some suggestions. Of course, more can be done. So the first one, we can do the study across the whole lifespan of battery, such as we can consider the degradation cost and also consider the recycling value of battery. And the second direction can be on the market. We know currently, I think the cost is a barrier for battery applications, and another barrier can be is market design. That is how you can design a market to make the benefits for both partners involved. So there's an example. We can consider the aggregated battery management. The last one we should consider, I think, the uncertainties from renewable generation, from loads, from the topology for robust solutions. So currently, if you consider the unbalanced, the techniques can be stochastic optimization, robust optimization, even there's another one called distributionally robust optimization. So there are many strategies to be used here. So this is the future work. Yeah, that's my presentation. Thank you for your time and also questions. Thanks.
Yeah, thank you very much, Sue, for the very good presentation. So now we are opening the floor for the questions from the attendees. Please. If anybody wants to ask a question, can you please unmute yourself and then ask the question? Okay, so probably I'll use this opportunity to start the first question, and that is mainly about that relationship between the penetration level of the photovoltaic systems and the mainly the defined location for the battery systems. Through your studies, did you see a significant difference when the penetration of the renewables, like the photovoltaic systems in your case studies, was increased versus the defined location of the batteries? I assume that probably the capacity might have changed, But what about the location? Was it significantly changed as well or not?
Good question. Actually, if you see case 5, in our study, not so much difference. But I have analyzed the reason. I think it's because of our definition of the CRSI, the Comprehensive Loss Sensitivity Index, and that is, I will show you up here. I will return to the definition. Yeah, here, the lambda D and lambda C, and how you set the value for this study. In our study, we consider the duration and the price impact. So we set the lambda D equals 0.6 and lambda C 0.4. So that means we emphasize more on the discharging. So in this case, the generation, the ejection, the penetration will be, the impacts will be limited. But I personally believe if you consider different settings of weights, the results can be different. And the higher penetration will have impacts on the locations.
Right. So it's mainly eventually going to be the utilities preference.
Yeah, if you see here, lambda D and lambda C, we see is 0.75, 0.25. So you emphasize on the lambda D.
Right. Okay. Yeah.
D means for the load, peak load area without penetration.
Yeah. Very much. Thank you very much. Thank you. Yeah. Any other questions from the delegates? Please feel free to unmute yourself and ask the questions.
Hello, I just have one question. When we are for implementing the batteries for like utility scale or commercial scale batteries, and if they are providing frequency control or ancillary service, and are batteries flexible enough to provide the required dispatch? I know they're like they have the power and energy limitations. So if can they provide the required frequency or voltage reserve?
Oh yes, of course. So as we said at the beginning, the battery has multiple functions. I think one of them is the frequency regulation, and I think it happens on the high voltage system. For the transmission system, the battery is big, and also for the isolated, as you mentioned, the microgrid, that's the isolated. You have the battery to support the system. So we'll adjust the power or energy of the battery outputs. The frequency will be adjusted. I think in SA, the Tesla project in South Australia, that's the main purpose is for the primary adjustment. But for our studies on the RV side of the distribution system, so this is a distribution system. It's connected to the grid, and the frequency by small scale battery, is limited. The adjustment. So we haven't considered this frequency surveys in our study. But if you change the location, if you change to the transmission or microgrid, frequency adjustment is one important area to consider.
Yeah, thank you very much.
Just one more follow-up question. So currently, for example, I see Tesla power bank. So they have their energy and power specifications. So are there any limitations that what the specified nameplate power and energy limits are and what the real time they can do? Is there any difference, like in the real time, can they be more flexible to that compared to the real their specifications?
Yeah, good question. Actually, these technical sheets of Tesla products are available on the website, and the capacity fixed, the power fixed. Yeah, also we consider, I mean, here in our study, we consider discrete variables to select. I mean, for the battery, it consists of different cells, different systems. That's the blocks, you know. So in our study, we can consider different combinations of the blocks. But for the real-time applications, their outputs can be adjusted, but very limited. You know, for the battery, it comes with the battery management system, BMS, and also the inverter control system. So the inverter control system plus the battery management system will control its outputs, will adjust its outputs.
Yeah, perfect. That's very useful. Thank you.
No worries.
Yeah, thanks very much. Any further questions from the delegates? May I have one question? I mean, and that's mainly about this unbalanced factor that we have. And you said that generally majority of the studies are, when they are talking about the battery placement in distribution networks, they are focused on, or they assume like a balanced system, but in reality, yeah, it is unbalanced. So the way that your technique is addressing that is that it seems you are conducting this sensitivity analysis per phase, and then so considering each phase separately, and then trying to average them and saying that this average represents the overall situation of the network. Is that correct?
Oh, yes.
Yeah, and can I ask, like, have you had any comparison between using assuming the network is balanced while it was unbalanced, and then comparing the result of that battery placement versus what your technique presents? How much do they differ from each other? Is it like a significant difference in either the location or the capacity, or yeah, there is a difference, but it's sort of marginal?
It is a good question. Actually, we have thought about this question before when we designed this case study. So, because this system, you know, is a real system, it's unbalanced. So, if you want to make it balanced, that means you have to, you know, average the loads and distribute it equally on 3 phases. And also, we have the phase, I think, missing in this network. So it's physically hard to do that because that will modify the network, the physical things. Yes, as you said, it is a good suggestion to consider this study on balanced system. But we haven't done this. I'm pretty sure the impacts will be obvious because, you know, if we consider 3 phases balanced, the module will be, you know, 3-phase balanced. That means that you have a single line representation of the system. But if you consider 3-phase, you will consider the component impacts, the phase difference, and yeah, I'm pretty sure that the result will be quite different. But we haven't tried this.
Right. Yeah. Thank you. Thanks very much. Any other questions from the delegates to the speaker? Okay, yeah, probably if there are no further questions, then probably we can thank the speaker for the very good presentation, very informative discussions that Dr. Su presented on the interesting topic of battery placement in unbalanced distribution networks and the new methods that have to be employed to consider that charging characters of the batteries as well as the unbalanced situations. So thank you very much. I hope everybody has enjoyed, same as me as well. That was very informative. And I know now it's in Sydney already close to 8 o'clock, so sorry that we are taking so much time from you. Yeah, thank you.
Thank you, Fahad, and thank you everyone for the time.
Yeah, thank you. So just as a final note, this was the 5th seminar that we had arranged by the Industrial Electronics Societies in WA in this year. And our plan is that we are going to have another seminar in the last week of next month as well. So like an information will be circulated through email to everyone. And we would love to hear from you, even if some of the attendees, they are interested in delivering one of the talks as in like in this series of seminars. We would love to hear from you, and please, if you can, just contact one of the members of the IEEE Society. My name is Farhad Shahnia from Murdoch University. So we would definitely love to arrange talks if somebody is interested to deliver a talk, and that would be fantastic. So again, let me thank everyone, the speaker and all the attendees. Thanks very much for joining this meeting, and have a good evening. Thank you.